Welcome to Empowered Learning. This video will be about the exposure and learning of the use of differentiation rules in calculus. What differentiation rules are is just a quick and dirty way to be able to take the derivative of some function without having to go through the actual definition of a derivative. And for those of you that are not familiar with what the definition of a derivative is, I'm going to write it here just so that you can see it. So when we take the derivative of a function, what we're really doing is doing the limit of the difference quotient of that function. And what I'm writing here is one of the many forms we could use to define that. Okay. Other forms. This is another form that could be used. And here we're assuming that a is a constant value. And so these two forms that you see here are the ones that are used the most. And I'll clean this one up here. But there are others. Essentially what we're doing here is we are trying to find the limit as the difference in between 2 points on a secant line. And you can just think of it as a line that intersects a curve of a function. As those 2 points get closer and closer to each other, they're going to theoretically get to a distance of 0 in between them. And at that point, you would have basically one line going through 1 point at one single location for a function. And what we call the slope of that line is the instantaneous rate of change. And so what differentiation rules are is just our way of saying, hey, for a function that I have, I don't want to go through this whole process of taking the limit of the difference quotient every time. For certain functions, we know that, hey, if I put this type of function in, the pattern is going to follow this way and I get this particular result out. And so we know that for some of our basic functions that we use. And so since we know that, we just say, well, let's just skip all of this and just go straight to, I know that the derivative of this particular function is going to be this function. And so that's what we're going to talk about. And that's what we're going to do examples on and trying to be able to use. Because from this point on, if you're looking at this video, probably from this point on in calculus or whatever it is that you're taking, you won't be doing this whole limit of the difference quotient thing again, unless you're doing some type of research or something. All right, so now that we know what differentiation rules are, notice that all the ones that I have checked here are going to be the ones that we're going to focus on in this video. And this is a part 1 series of this video, because I'm just going to go through how to basically take the derivative of functions. The part 2 video you'll see examples of how we actually use this in some very light applications. Okay. All right. So let's start off with the first differentiation rule. And this just says that the derivative of any constant is 0. Okay. Now, if we think about what that means conceptually, let's say I had the horizontal line y is equal to 2. Okay. If I draw that line, it looks like this, where all the y coordinates for any point on that line is going to be 2. Well, we know that the slope of that line is 0. Okay. And it doesn't matter whether it is y equals 2, y equals -2, y equals 1,000,000, y equals -3 billion. All those particular lines have a 0 slope. And of course, the derivative, which is instantaneous rate of change or slope of tangent line, if you want to call it that way, of all those functions are going to be 0, no matter what. Okay. And so we don't want to forget that whenever we're taking the derivative of a function, what we're really doing is finding the slope of its tangent line, and or trying to find the instantaneous rate of change of the function. All right, so for number 2, what we see here is that we're taking the derivative of a constant multiple of some function, and all this says here is that I can ignore the constant and take the derivative of the root function. So pretty simple. Number 3 and number 4 are pretty simple as well. If I want to take the derivative of the sum or the difference of two functions, then I just take the derivative of each of them separately and then either add the two answers or subtract one answer from the other. These next two rules are what we call the product rule and the quotient rule. And I'm going to talk more about this when we get to some of the examples where we actually need to use it, but I'm just going to give an overview now. So in general, what the product rule says is that if I have a function that is made up of the product of two other functions, meaning I take one function f and g and multiply them together to create the new function, then the derivative is not going to be take the derivative of the first times the derivative of the second. It doesn't work like that. What we have to do is take the derivative of the, and the way this is written, the derivative of the second function times the first plus derivative of the first function times the second. Okay, and we could write this the other way as well. We could say that this is the derivative of the first here times the second plus derivative of the second function times the first. Okay, you could write it that way, or how I actually like to do it is I like to leave the f's and the g's all in the same place here. This is my personal preference here, where I say derivative of the first times the second plus first times derivative of the second. So I leave f and g the same, and the one thing that I change is where I have my prime sign to do the derivative. So just remember, derivative of first times second plus first times derivative of second. Or you can put it in any order that you like, as long as it's following the same rule here and you get this result. Doesn't matter how you put it. All right, so for number 6, we call this the quotient rule. And this is how we take the derivative of the quotient of two functions, meaning one function divided by the other. Now, for this particular rule, please note that for a derivative to exist here, we can't have our function g of x here equal 0. That can't happen. If it does, then our derivative is not going to exist. Okay. Now, we see here that this says we have g of x times the derivative of f of x minus f of x times the derivative of g of x all over g of x squared. If we look at the f of x function as the high function and g of x function as the low function, then we could reword what we're saying here this way. We will have low derivative of high minus high derivative of low over low squared. Okay. Now, to put that in a more succinct way, we could just say this: low d high minus high d low over low squared. And I'll say it again: low d high minus high d low over low squared. And so what I suggest that you do here is to go over what I just said about 4 or 5 times to make sure that you remember the pattern here. So again, low d high minus high d low over low squared. And every time you say d, you're going to take the derivative of whatever function comes directly after that. All right. So rule number 7 here, the chain rule, we're not going to go over in this video. I do have other videos for that. So if you search for my videos and type in chain rule, you'll see that. So the power rule is probably one of the most important differentiation rules, because it tells us how to take the derivative of a power function. And a power function is just something x raised to the n, where x is a variable, n is a constant. And so here, what we essentially do is whatever the exponent is, we multiply it out in front, and then we subtract 1 from it. So to give you a quick example of what that looks like, let's say I wanted to take the derivative of x to the 4. Okay. So if I take the derivative of that, and I'll write it in the Leibniz notation as well, just so that you know these two are the same, then we just take the exponent here, put it out in front, and then from that subtract 1 from the exponent. And that's how we end up getting 4x cubed. All right, so rule number 9, the derivative of e to the x is just e to the x. And this is my favorite one because I don't have to remember anything, okay? The derivative of e to the x is just e to the x. And so this is one of the reasons why when we talk about exponential growth, exponential decay, compound interest, and anything that population growth, population decay, or anything that grows or decays exponentially, it is modeled by this function. And so this function is special in that it is a function that can track its own rate of change. Okay, and that's part of the reason why we use it in so many different applications. Now, the general form for this is number 10, which we won't go through and talk about in this video. But what I do want you to know here is that if we let a equal e here, then we would have the derivative of e to the x is e to the x times natural log of e. And if you remember from your pre-cal courses, we know that natural log of e is just 1. So the point that I'm trying to make here is that this derivative is a special case of number 10. All right, so I won't be talking about 11 or 12 here because I'll cover that in my videos on logarithmic differentiation. But we do need to talk about the trig function derivatives. And so we see here that the derivative of a sine function is a cosine function, and a derivative of a cosine function is minus sine. And then from here, to find the derivatives of the rest of these, we essentially employ the quotient rule. Okay, so for instance, I'm going to take the derivative of tangent and write it in terms of sine and cosine so that you see that it's actually equal to secant squared here. So here, if we take the derivative of tangent, tangent is going to be the derivative of sine divided by cosine. And if you remember, in general, if I take the derivative of the quotient of two functions, remember that it is low d high minus high d low over low squared. And so we are going to use that here to figure out that the derivative of tangent is going to be secant squared. So the low function is cosine, the high function is sine. So if I say low times derivative of high, and I'm just going to write it all in prime notation here, minus high times derivative of low, and all that over low function squared. So if I finish up here, I know that the derivative of sine is going to be cosine. So I'm going to have cosine x times cosine x, which that essentially is just going to be cosine squared. So I'll go ahead and write that and erase this. Then we have minus sine times the derivative of cosine is minus sine. So we see there a minus sine times a minus sine is going to be a positive sine squared. So I'll go ahead and rewrite this. And all of that will be over cosine squared. Now, if you remember, one of the fundamental identities in trig here is that we have sine squared plus cosine squared is equal to 1. So we know that that's an identity here. And of course, the reciprocal of cosine, or 1 divided by cosine, is secant. So that means that the reciprocal of 1 divided by cosine squared will be secant squared. Okay. And so if we go back here, we see that the derivative of tangent is indeed secant squared. And so the reason why I wanted to show you that is that for tangent, cosecant, secant, and cotangent, we can do the same thing that I did here for all those functions when we take the derivative of it, and you can derive what its derivatives are. So the point I want to make here is that if you're the type that, hey, I can't remember a lot of stuff like me, then what you could do is memorize the derivative of sine is cosine, memorize that the derivative of cosine is minus sine, and then everything else, if you can't remember it, just derive it by using the quotient rule. Okay. So now to close us out here before we actually start doing some examples, here, just like we talked before, the derivative of tangent is secant squared. We know that the derivative of cosecant is going to be minus cosecant cotangent. The derivative of secant is going to be secant tangent. And I'm just saying that for short. It's really secant of x times tangent of x. And here it's minus cosecant of x times cotangent of x. And of course, the derivative of cotangent is negative cosecant squared. And again, we could just use the quotient rule here and rewrite these functions, tangent as sine over cosine, cosecant as 1 over sine, secant as 1 over cosine, and cotangent as either cosine over sine or 1 over tangent. So either way. And you can get these derivatives here. All right, so now what we are going to do is go over several examples to where all of the rules that I've talked about here that I said we were going to cover will be used. Okay, so for our first 3 problems here, these will be relatively easy for us. This first one here, we actually want to take the derivative of all of them, but for this first one here, notice that we have a constant. And what we know here is that if we take the derivative of a constant, the derivative of all constants are going to be 0. Okay, so this is a pretty simple one to do. Okay, so for our second function here, we want to take the derivative of that. And here notice that our first term, we have a first term minus a second term plus a third term. And if we go back to our differentiation rules, notice that rule number 3 and number 4 tell us that, hey, if I have a sum or difference of 2 functions and I want to take the derivative of it, I just take the derivative of each of them separately. Okay, so in this case, I want to take the derivative of each term separately. Also notice that for the first term here, I have a 1/2 multiplied by t raised to the 6. And for the second term, I have a 3 being multiplied times the t. And if we look back here, we see that rule number 2 basically tells us that I can ignore those constants, take the derivative of the root function. Okay. So going here, I'm going to ignore the 1/2, and then I'm going to take the derivative of t raised to the 6. Well, the rule that goes with that is going to be our power rule, number 8 here. And so we basically take whatever the exponent is, put it out in front, and then subtract 1 from the exponent. So if we do that, that'll be 6 times t raised to the 6 minus 1. And I'll clean this up in the next step. For the next one here, we just take 3, and then we take the derivative of t. And of course, the derivative of t is just t raised to the 1. So we literally here have 1 times t raised to the 1 minus 1. Okay. And then, of course, here the derivative of any constant is going to be 0. Now, if we clean all this up, we see here that 1/2 times 6 is 3. And we see that 6 minus 1 is 5. So our first term is 3 times t raised to the 5. Minus, we see that 1 minus 1 is 0, and anything raised to the 0 here, other than 0, is 1. So all this is 1, and 1 times 1 is 1. 1 times 3 is 3. Okay? And of course, anything plus 0 is just itself. So our final answer here will be that the derivative of this function is just 3t raised to the 5 minus 3. Okay. Now, in saying this, one thing I want to go ahead and mention here is that for this term specifically, if we're taking the derivative of this particular term here, because this comes up so often, we normally don't really apply the power rule here. We just know that the derivative of any constant times a variable is just going to be whatever that constant is. And if we conceptually think about it, if I was to draw the line y equals 3t, it would look something like this. Okay, and we're assuming here that this line is going through the origin here. The slope of this line would be a -3. So that means any point that is on this particular line, if I want to figure out what's the rate of change of it, is going to be the same thing. It's going to be the rate of change of that function at any given point instantaneously is going to be -3. So that's why anytime we have a linear function here, the derivative of that linear function is just going to be the slope of that particular linear function, or the slope of that line. Okay, so we want to keep that in mind. All right, so let's move on to number 3. So for number 3, we want to take the derivative of this function here. And notice that for the first term, we have a constant multiple here, so we're going to ignore that for now. And then we're going to multiply this times, we're going to multiply it times the exponent here. So let me clean this up. So this will be 5 times -3/5 times t raised to the -3/5 minus 1, because we're doing the power rule. Okay. Now, notice that here, the next term is a 7. And of course, the derivative of any constant is going to be 0. Okay. So here, I'm going to try to fit it in here. It's just going to be plus 0. So all we're really worried about here is this first term. Okay. So if we look at it that way, here I have 5 times a -3/5. These 5s here will reduce to 1, and all I'll have is a -3 left. I have t raised to the -3/5, and I need to subtract 1. Well, that's like me subtracting 5 divided by 5 here. So I'm going to move this 1 out the way here for a second. And we'll come here and say this is -5/5. And of course, in the numerator, in the exponent, that result is just going to end up being -8/5. And so we see that the derivative of our function here is -3 times t raised to the -8/5. Okay. Now, please note that I can actually rewrite this in root form and simplify it if I wanted to. But just as a general rule of thumb, if your function like this is given in fractional exponents, then you want to give the actual answer of the derivative in fractional exponents. If it's given in root form, then you want to give the answer in root form as well. Okay. So for instance, if this particular function was written as 5 times, well, let me give myself some more room here. If this was written as 5 divided by the 5th root of t cubed, okay, if it was written like that, then you could work this out, and then at this point what you would want to do is translate this back into, you know, root form. And so this would be like 3 raised to the 5th root of t raised to the 8. Okay. And of course here, since you have t raised to the 8 in the denominator, you could simplify this some more, because you have 5 t's inside of here that would equate to 1 going out. So this would be like t times the 5th root of t cubed, if you simplify that. And here also we could simplify this, and this would be like 5 divided by t times the 5th root of t squared, if you really wanted to get technical. But it's more convenient for us to write it this way so that I don't have to do the product rule down here in the denominator. Okay, so that's the reason why the function was written this way, to make it easy. All right, so let's look at the next few examples here. All right, so the next 2 examples we are going to do here, this one for number 4, one of the reasons why I'm doing this one is to make sure that you know that whenever you do have something in the root form, you do want to translate it to fractional exponent form before you take the derivative using the differentiation rules. So here we know that square root of x is just x raised to the positive 1/2. And here this is 1 divided by square root of x. So this part here is like having x raised to the positive 1/2 in the denominator. But if we do 1 over that, that's going to end up being x raised to the negative 1/2. Okay. So that is what this would end up being here. And this is an equivalent way of saying square root of x minus 1 divided by square root of x. Now, at this point, when we take the derivative of it, we're taking the derivative using this. And one of the things I want to stress, especially if you're actually taking a calculus course and you're looking at this video, please, 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 with sugar on top, pretty please, make sure that you label when you're actually taking the derivative. Okay. As an educator, one of the things that we really can't stand as educators is when students actually are taking the derivatives and they don't give us a clue to say, all right, well, when did your actual function that you originally dealt with stopped? And when did you start taking the derivative? They just kind of make everything all equal, and that's not correct. So you do need to state when you're actually taking the derivative, because it makes it easier for others, especially educators like myself that may possibly be grading your papers, read what you're trying to write. Okay. All right. So here, if we are going to take the derivative of this, then of course we'll use the power rule. So power rule says we take whatever the exponent is, multiply that in front, and then we subtract 1 from the exponent. And then we'll repeat the process here. So we have a minus, and then there's a negative 1/2, x raised to the minus 1/2 minus 1. And notice here for fraction, we can write 1 as 2 over 2 to make life easy for ourselves. Let's try to write that one over. And so now this just means that I have 1/2 x raised to the minus 1/2 here. And this is plus 1/2 x raised to the minus 3/2. And so from here, technically you're done, but we want to try to get this back into root form because it was given to us in root form. So here this would be 1 divided by 2 times square root of x. And this would be plus 1 divided by 2 times square root of x cubed. Okay. And so from here, again, you could try to simplify this some more to make it a little bit more succinct. That's really not the purpose of this video, so I'm just going to leave it. But I will say that if you're using the derivative of some function in an application, then you really want to try to simplify it in its most simple form, just because it will probably make the math easier for you once you use that derivative in whatever else that you're going to use it in. All right, so let's look at example 5 here. Now, example 5, if you notice, this is a composition function, okay? Which means we have a function, mainly 1 plus 2x, stuffed inside of another function, mainly something squared. And normally we just say x squared. Now, note that one way that we can actually do this derivative here is to use what's called the chain rule, okay? And this, the chain rule is the strategy for how to take the derivative of a composition function. But again, that's not the focus of this particular video. So I'm just mentioning it for those of you that are sort of familiar with what the chain rule is. Know that I'm not going to solve the derivative this way on purpose, okay? So since we don't have the chain rule at our disposal here, or we're choosing not to do it, then the only other choice I have here is to go ahead and figure out what this is going to be by multiplying this binomial squared out, okay? So this is like multiplying this times itself. And just for clarity, I'm going to do this the long way. So this is like multiplying 1 plus 2x times itself. So if we do the for method here, 1 times 1 is 1. 1 times 2x is 2x. We got the same thing here on the inside. And then 2x times 2x is 4x squared. And so this is what our resulting function is. So y is going to be 1 plus 4x plus 4x squared. So if I take the derivative of y, remember that the derivative of any constant is what? Yep, that's right, 0. Plus, we take the derivative of 4x. If you remember, if we take the derivative of any linear expression here, it's just going to be the derivative of, it's just going to be the constant. That's going to be the result. And I'm going to scroll back up here. Remember how we did the minus 3t raised to the 1, and we did all that and just end up being negative 3 here. And I told you here that anytime we take the derivative of a linear expression, this ends up being minus 3. Well, that is the situation that we were faced with here in this particular example, or this term rather. All right, so for the last one here, we have 4 times x squared. We ignore the 4, and we just take the derivative of x squared. And again, we just put the exponent out in front, then subtract 1 from the exponent. And once we do all this, we end up just getting 4 plus 8x, because 4 times 2 is 8. 2 minus 1 is 1, and x raised to the 1 is just x. All right, so let's do examples 6 and 7 here. Now, examples 6 and 7 involve us using the product rule and product rule and quotient rule respectively. So for number 6, we're going to use the product rule. And for number 7, we're going to use the quotient rule. Okay. All right, so for the product rule, I'll go ahead and rewrite it here. If we have the product of two functions and we take the derivative of it, we take the derivative of the first times the second plus first times derivative of the second. Okay. And actually, I'm going to rewrite that since I already have this name g of x. I'm going to write it in terms of u and v, just so that it's not confusing here. So if I have product of two functions u and v, it will look like this. So we're going to let square root of x be our u and let e to the x be our v. And to make life easy for ourselves, we're going to rewrite square root of x as just x raised to the 1/2. So now this is my u, that's my v. So if I take the derivative of g of x, then that means I need to take the derivative of x raised to the 1/2 times e to the x. And then I have x raised to the 1/2 times derivative of e to the x. If we remember the power rule, the derivative of x raised to the 1/2 is just 1/2 x raised to the 1/2 minus 1. And then all that times e to the x plus x raised to the 1/2. And remember that this is my favorite derivative here. The derivative of e to the x is just what? Yep, that's right. It's just e to the x. It is itself. And so here, all we have to do is simplify. So we remember last time that this was the same as 1/2 x raised to the negative 1/2 times e to the x. And this is x raised to the 1/2 times e to the x. And so technically we're done here, but again, we were given this in root form, so I want to get it back in root form. And since that is the 1/2 x raised to the negative 1/2 is just 1 over that, but 1 times e to the x is just e to the x. So I'm going to put this over e to the x plus square root of x times e to the x. And so technically we could stop there. Since I have a common factor of e to the x in both, I'm just going to go ahead and go one step further and just write it like this. And so it's okay to stop here, but you also can write it that way. So that is how we would use the product rule to take the derivative of a function that's made up of two functions being multiplied together. All right, so let's look at example 7 here. So remember, for example 7, we're using the quotient rule, okay? And for the quotient rule, we had a little saying that we did to try to remember it, and I'm going to rewrite it and say it here. So if we have the quotient of two functions and we're going to take the derivative of it, if we look at f as the high function and g as the low function, then it's going to be low d high minus high d low all over low squared. Okay. And so if that's the case here, just know that 2t is going to be your high function, and 4 times t squared is going to, 4 plus t squared is going to be your low function. So if I'm taking the derivative of this function here, then my low function is 4 plus t squared times derivative of the high function minus high function times derivative of the low function. And then I'm going to take all of that and do the low function squared. Now, before we move on, one thing that I do want to say here is that whenever we take this, the square of the low function, you do not want to multiply this out, okay? And so you'll see that a lot of times we may end up having to use one of these factors here to be able to reduce another factor that's common in all the numerator variables to 1. Doesn't always end up being that way, but even in application problems, it's probably better to leave it in this factored form versus trying to multiply it out. So if you can, just leave it this way, okay? Now, if you have an instructor that specifically says that, hey, they want all this stuff multiplied out, then do so. But normally speaking, if you're going to use derivatives for applications, you want to leave this denominator here in its factored form. All right, so with that being said, let's go ahead and move on here. So we got b prime of t. Doesn't look very good. b prime of t. And so we just got 4 plus t squared. We take the derivative of 2t, and we know from earlier, derivative of any linear function or expression is just the slope of that, which is 2, minus 2t. And if we take the derivative of 4 plus t squared, the derivative of any constant is 0. And the derivative of t squared is just going to be exponent times t exponent minus 1, or just 2t. And then all that, and we just rewrite what we have in the denominator, not multiplying it out. So from here, we are essentially done as far as executing the derivative, but now what we want to do is clean things up, okay? So here, we'll distribute to both terms here. So this will be 8 plus t squared. And here this would be just a minus 2t times 2t, basically, because this is just 2t. And this is 0 here, so we can ignore that. So it's just 2t times 2t, which will be 4t squared. And all that over 4 plus t squared, quantity squared. And then all we need to do now is just simplify the numerator. And if we do that, that would be 8 minus 2t squared. All that over 4 plus t squared, and entire denominator squared. And so we could factor out a 2 out of the numerator if we wanted, but it's not going to really change much for us here. So you could write it like this if you wanted, but here is where it is acceptable to stop. All right, so let's look at our next few examples. All right, so for example number 8 here, part of the reason why I have this particular problem in here is that it could be done a couple of different ways. When you see this, the first thing that you think is, hey, I have a function multiplied times another function, and I could use the product rule for that, which is very true. You can do that. Another way that you can do this same problem here is by actually going ahead and distributing first. And I'm not actually going to work it this way, but I'm just going to do a little bit so that you can see the similarities and differences here. So remember that this w here is like w raised to the 1. And of course, since we have two exponential expressions here where the bases are the same, we can add the exponents. So if I add 3 halves plus 1, or 3 halves plus 2 halves, that's going to be w raised to the 5 halves for that first term. For the second term, c is assumed to be a constant. And so we're just going to have c times w raised to the 3 halves times e raised to the w. Okay, so this is what z of w will be. In this case, notice that you end up having to take the derivative of this first term plus ignore constant, and then you take the derivative of the product of these two functions. So my point here is that you end up having to do the product rule anyway, okay? And so it is your choice. You can decide that you want to distribute these terms here, do this one by itself, and then do the product rule on just this, or you can just do the product rule on both of these to start off with. I know for me, I like to do things as most efficient as possible. So what I'm going to do is just take the product rule of whatever was given to us from the beginning. But again, if you do it the other way, you should get the same exact answer that we would doing it this way. All right, so Here, if I was to take the derivative here, I'm going to take the derivative of the first function times the second plus first function here times derivative of the second. And remember, c is a constant here. So if we do that, then derivative of z of w, here this is just going to be 3 halves w raised to the 3 halves minus 1. I'm going to write 1 as 2 over 2 here. And all that, here, all that is going to be times w plus c e raised to the w plus, I have w raised to the 3 halves here, and I'm going to take the derivative of these two terms. So taking the derivative of w with respect to w is the same as saying this, derivative with respect to w of w, just like saying the derivative of x with respect to x. This is a linear expression here, so the derivative of it will be whatever the slope is, and since we don't have a number here, there's an understood 1 there, so that would just be 1. So the derivative of w with respect to w would just be 1 plus, ignore the constant, and of course the derivative of e to the w with respect to w is just itself. Okay. All right, so let's erase this and then we'll finish up what we have here. So at this point, we're technically done with actually executing the derivative part. Everything else that we're going to do for the most part after this is just cleaning up our function to make it look nice. So this is going to be 3 halves w raised to the 1 half. That's what all that is. W plus c e raised to the w. And this is w raised to the 3 halves. I'm just going to rewrite all of that. Okay, so at this point, what we would probably want to do, we have a couple different options here. We could actually just say, well, hey, I have in common a w raised to the 1 half in both of these terms here. We could do that and then just multiply the rest through. But what I'm going to do just to kind of make life a little bit more simple for ourselves is just distribute these two terms here, distribute these two terms there, and then just leave it alone. And kind of let you deal with how you would want to simplify that or rewrite it in another way. So for this first term, we'll have 3 halves, w raised to the 1 half times w raised to the 2 halves would be w raised to the 3 halves plus 3 halves c, w raised to the 1 half, e raised to the w. And then here we would have w raised to the 3 halves plus c, w raised to the 3 halves, e to the w. And so here, without doing any more simplification, would be your final answer to this particular question, or for the derivative of it. All right, so for example number 9, notice that we have e to the x divided by x. We could use the quotient rule, or we could use the product rule. And so I say we could use the product rule because remember this is 1 times e to the x, and I could rewrite this as x raised to the negative 1 divided by e to the x. And so if I did it that way, I would use the product rule very similar to how I did it here. Since I would like to showcase the quotient rule, I'm going to do it that way and using the quotient rule. But I do want to let you know that yes, you could do this problem also using the product rule. All right, so keeping it this way here, we're going to call u the high function, v the low function. So we know here that the derivative of f is going to be low function derivative of high, or low d high, minus high d low, all over low squared, okay? So in noting that our low function here is x, the derivative of our high function, the derivative of e to the x, is just e to the x. So I'm going to skip actually writing that with the prime and just do it. High function is here. And derivative of a low function, remember that the derivative of any linear function or any linear term is just going to be the slope. And that slope in this case is just going to be 1. Now take that and divide that all by the low function squared. Okay. So from here, since I have a common factor of e to the x, I'll pull that out. And then I just have left x minus 1. And all that can be divided by x squared. And this is a nice, simple, compact way to leave your answer there. All right, so let's look at our next 2 examples here. So again, we have situations where we need to use the product rule for number 10. And for this one, you would only want to use the quotient rule for this one, okay, for number 11. So let's focus on number 10 first. So if we take the derivative here, well, first, let's rewrite this. So square root of x is just x raised to the 1/2. So that will be x raised to the 1/2 times sine. Here we would take the derivative of the first function times the second plus first function times derivative of the second. And here we know that the derivative of x raised to the 1/2 is just 1/2 x raised to the 1/2 minus 1. All that times sine x plus x raised to the 1/2. And derivative of sine x is cosine x. Okay? And that comes from this particular rule here. All right, so now that we have this, we know that this first term is just going to be 1/2 x raised to the negative 1/2 times sine x. Oops, yeah. And this will be plus x raised to the 1/2 times cosine of x. And so from here, since we were given our problem in root form, we will translate it back in root form. And we see that our final answer ends up just being 1 divided by 2 times square root of x times sine. Or if you wanted, you could just put sine x over 2 times square root of x plus square root of x times cosine of x. So this would be your final answer for that one. All right, so for number 11, we'll use the chain rule again, the quotient rule again, where our function on top is going to be the high function. Function on bottom is going to be the low function here, okay? And I'm going to put this in terms of u and v here. So if you remember, derivative is low d high minus high d low, all over low squared. Okay. So here we take the derivative and we get some separation here. So the derivative of the low function times derivative of the high function minus high function times derivative of the low function. All that divided by low function squared. And remember here, we do not want to multiply out the denominator function. We don't want to expand that. All right. So here, I'm going to switch colors here for a second. We know that the derivative of 1 is going to be 0. And we know that the derivative of sine is going to be cosine. So that takes care of what the derivative of that is. Here, we know that the derivative of x with respect to x is 1, and the derivative of cosine of x with respect to x is minus sine. So all of that would be that. And so just to remember here, the derivative of any constant is 0. The derivative of sine is cosine. The derivative of cosine is minus sine. So now that we have that, we can now try to clean this up here. So we have x times cosine of x. And that's going to be multiplied times another cosine of x. Minus. And notice here we have a 1 plus sine x here. And I know that doesn't look that great. I'll clean it up. So we had a 1 plus sine x here. And that's multiplied by 1 minus sine x. And so you can think of this sort of as a plus b times a minus b situation here. Yeah, that didn't turn out real well. And remember that a plus b times a minus b is just a squared minus b squared. So here in parentheses, what we're going to do is just a squared minus b squared. Now for our a here, we see that a is going to be 1. So 1 squared is just 1 minus b is sine, so we're just going to say that that's sine squared. And we take all that divided by what our denominator was again. All right, so here, notice that our 1 minus sine squared, that is a trig identity. And we know that 1 minus sine squared, all of this is just cosine squared. Okay. And we want to remember that because when we finish working on the numerator here, we're going to see that we're going to have some terms in the numerator to cancel out. So if I go ahead and distribute my cosine here to both terms, I'm going to have x times cosine x plus cosine squared x. And then here minus the same cosine squared x. And all of that is going to be over x plus cosine of x, quantity squared. And here we see that both of these terms cancel to 0. So that means our final answer here is just going to be x times cosine of x all over x plus cosine of x quantity squared. All right, so let's look at our last two examples. All right, so for example number 12 here, notice that we just have the sum of two functions, and of course one of them has a cosine in it, well, one of them has a sine in it. So here we know that the derivative of the first term, we just ignore that constant. Just trying to get this to, we'll just start over. So s prime of t. So we ignore the constant, and we know that the derivative of cosine is minus sine. And of course, the derivative of sine is cosine. So final answer here just ends up being a minus sine t plus 3 cosine t. Okay. And that one's pretty simple, so we'll just box it off. All right, so for our last example here, we see that we have cosecant theta multiplied times theta plus cotangent theta. And I know I haven't been writing it here because we've been doing prime notation, but note that whenever I say the derivative of y with respect to theta, that actually means this, okay? And also note that what we're going to be doing here is using the product rule. So if I let this be u and let all of that be v, then this is going to be derivative of first times the second plus first times derivative of second. So here, if we go ahead and work that out, and I'm going to come down here to do it because I'll have a little bit more room. So let's say dy d theta. Here I know that if I look at this, the derivative of cosecant is going to be minus cosecant theta cotangent theta. And if we look back here, remember, derivative of cosecant x is minus cosecant x cotangent x. And so we just replace our x's with thetas. So this would be minus cosecant theta times cotangent theta. And then that will be multiplied times the other term here, which is just theta plus cotangent theta, plus, now we just have cosecant theta, that is our u, and we're going to multiply that times the derivative of theta plus cotangent theta. Remember that taking the derivative of theta with respect to theta is just like taking the derivative of x with respect to x. So that is just going to be a 1 here, because that looks like a linear function to theta. If we take the derivative of cotangent, that is going to be negative cosecant squared. And so if you remember here, derivative of cotangent is negative cosecant squared. And I'm purposely leaving off the variable there and saying it just to make it quicker to say. But we do have to write the variable in. Okay. All right, so at this point, what we want to do is we want to go ahead and try to do what we can to simplify as much as we can. And the easiest thing that we could do here for this first term here is just to multiply, basically distribute this negative cosecant theta times cotangent theta to both terms here. So I'm going to do this. it's going to be negative cosecant theta, cotangent theta times theta. This is going to be minus cosecant theta. And since I have two cotangents here being multiplied times each other, there's going to be a cotangent squared theta. All right, so for our second term, notice that this 1 minus cosecant squared theta here is actually a trig identity. Okay, and what this actually ends up being is a minus cotangent squared theta. And if you've forgotten, all right, well, how did you get that? I'll go ahead and explain that quickly here. So in order to know that 1 minus cosecant squared, and I'm just going to do x here, is minus cotangent x. So recall here that sine squared plus cosine squared is equal to 1. And this is what's called the fundamental identity. It actually comes from the definition of a unit circle, and you just replace the, and I'll write that here, have the unit circle here. And if you replace x with cosine of some angle here, and replace y with sine of some angle, then you get this identity. So that's where that comes from. So here to get this in this form, we need to divide both sides by sine squared. Okay. And if I do that, then here sine squared divided by itself is just 1. Cosine squared divided by sine squared is cotangent. And 1 divided by sine squared is cosecant squared. And so now you can see all we need to do is algebraically rearrange this equation to solve for 1 minus cosecant squared. And if I do that, I subtract cosecant squared on both sides, subtract cotangent squared on both sides, you see that we get this identity here. So that's where that comes from. So doing all this to basically say that now we have minus cosecant theta times cotangent squared theta. Okay. And so from here, may not notice this, but notice that this term and this term are exactly the same. Okay. So since both of these terms are the same, I can combine them into one single term. And so my next step here would end up being, hate it when it delays like that. This would be a minus cosecant theta, cotangent theta times theta. And then here this would be a minus 2 cosecant theta cotangent squared theta. And so now at this point, notice that both terms has in common a cosecant theta and a cotangent theta. So this term has actually a minus cosecant theta, cotangent theta. This term actually has a minus, a cosecant theta, and 2 cotangent thetas. So if I factor out minus cosecant theta, cotangent theta, then in the first term, all I'm going to be left with is theta. Okay. In the second term, since I also factored out the minus there, this is going to be plus. And this cosecant is gone, and one of those cotangents are gone. So all that's left is another cotangent. And so from what we see here, this would be our final answer. And it would be in a nice compact form to where if we were to actually use this in some kind of application, this would probably be the best way to write it. And so we would want to leave it in the form that you see it in because of that. All right, so this concludes the part 1 series of this differentiation rules video. The next video that I will do to conclude this topic here will be doing actual application examples using these differentiation rules. And so I'm going to do some with just the algebraic ones, going to do some with the the trig function derivatives as well. Okay, so I hope to see you in that next video. Take care.